Hello everyone. Today we will continue discussing our topics in electromechanical energy course. So last class we had a quick revision for the power measurements. How can we measure the power using 3 watt meter and 2 watt meter methods? And we made also revision of the 3-phase and power calculations in 3-phase. So the topic today will be the magnetic circuit. So let me maximize. Okay, yeah. So the topic today, guys, is magnetic circuit. Magnetic circuit. You already learned something about magnetics in different courses. So I assume you learned something about electromagnetic with Dr. Lu in the course electromagnetic or electromagnetics, okay? But maybe from the point of view of communication, not from the point of view of high power. And also you may learn something about coupling in electrical circuit, but for the concept of magnetics in electromechanical devices, the basics are the same, like any magnetics you learned before. However, we will elaborate more in how can we have magnetics to operate electromechanical devices. So this is the concept, and we need to understand how much power and energy we can have in the magnetic circuit and we can store in the magnetic circuit. So this is the concept in our discussions. So it's a bit different compared to what you already learned before. However, we will give you like refreshment for the basics you had before, and then go ahead and continue discussions in some advanced topics. So the objectives of these materials, we may cover it in like 2 sessions, maybe. So today, maybe 1/2 of this material will be covered. So the objectives are going to be recognize the importance and application of magnetic circuits, how the magnetic circuit is important, and what are the magnetic circuit applications. To know the magnetic parameters, what are the magnetic parameters, the different parameters or relations parameters we have in magnetics, and also to know the magnetic circuit components. So like we have electrical circuit, you know, electrical circuit has resistance, has inductance, has capacitance. So what about magnetic circuit? So in electrical circuit, you had some circuit parameters connected in series or connected in parallel or series parallel, along with power supply, voltage source, current source. So this is electrical circuit. Do we have something similar in magnetics? So we will discuss more about the magnetic circuit and also what's called analogy between magnetic circuit and electrical circuit. So these are the objectives of our topic in electromagnetics or electromagnetic devices. So let's start, guys, from the basics you learn about the magnetics and what is the importance of magnetics. So firstly, magnetic circuits. Why do we need to know magnetic circuits? The magnetic circuit, guys, is the basic component of any electrical machine. So in electrical machines, the magnetic circuit may be formed by ferromagnetic material. So the ferromagnetic material is the magnetic material that will allow the flux to move inside this material. We call it ferromagnetic material. Like what material? Like cores that we have, for instance, in transformer. So I know you learned something about transformers before in electrical circuits. I wish if all of you guys attend the electrical circuits with me before. I'm not sure if all of you attend the course of electrical circuit with me or with another instructor. but I'm teaching a more detailed transformer in my course. So if you didn't have the transformer in details in the electrical circuit one, I have to repeat this part here in my course. But if all of you have attended electrical circuit with me, so most probably you will be aware of the main parts of the transformer and the different tests we have in the transformer. And in this case, in the topic of transformer, we may get more advanced discussions about three-phase transformer, not single-phase one. So the core that we have in transformer is nothing but a magnetic circuit. Also, magnetic material in conjunction with air medium. So sometimes we may have air gaps between magnetic cores. So what is the benefit of having this air gap? We will see this in our class. We will calculate the energy or the power in the air gap by means of voltage current here in these classes. And later on, when we discuss electrical machines, you will see how the power is transferred through the air gap. So the air gap between the core materials or the core parts can store energy, and we will make some calculations for that in our class today or next session. So along with the magnetic core, we have also some air gap between, or air medium. So this air medium will be used to allow some magnetic cores to move, and we will see how the magnetic cores will be moving because of the force we have, okay? And this is nothing but the electrical machines. So we can create from the cores or the magnetic circuits, we can create motors. So this is one direct application to magnetic circuit, having rotating machines. So rotating machines means you have a stationary part and another part moves in rotational motion. You may have also translational motion using magnetic circuit as well. So it could be rotating machine or linear machine, and all of them are exist in our life. So rotating machines, I think all of you guys are aware of motors. For sure, you could see before motors somewhere or generators somewhere in any place, the rotating motor. But the linear motor, you may not be aware of how the linear motor is, but the main application of these linear motors are in fast trains. So we use it linear induction motor, linear synchronous motor. We use it in fast trains, and all of these motors are based on magnetic circuits. So this is, guys, how the magnetic circuit is very important and what are the applications of the magnetic circuit. Also, in most electrical machines, except permanent magnet machines, the magnetic field or flux is produced by passing an electrical current through coils. So this is called electromagnet. Electromagnet. So we have permanent magnet and electromagnet. Permanent magnet means it has stored magnetic energy inside. So it's permanent. It's working and can make attraction for metals, okay? As we will see in the next couple of slides. It can make attraction for metals or for ferromagnetic materials, not all metals for sure. And this is permanent. It's not for a temporary time. But electromagnet is working or can attract the magnetic materials just if it is supplied by electricity. So we call it electromagnet. So in most of electrical machines, we have these electromagnets, except the permanent magnets machines. So in electrical machines, guys, we will see, or we already had a discussion before in the introduction. We knew that we have what's called permanent magnet synchronous machine. We have some permanent magnet motors, and we have field-based machines. So we will discuss these topics more in deep when we start in the synchronous machine topics and in the induction machine topics as well. So now we may have permanent magnet and we may have electromagnets. So again, permanent magnet, this is a natural material. We do not need to supply it by electricity in order to have magnetic field. However, permanent magnet, we have to supply it by electricity in order to have a magnetic field. And we will see some examples today for these magnets. Let's start, guys, discussing the concept of magnetics from the permanent magnet. I think all of you are aware of permanent magnets, and you could see that hundreds of times before. So the magnetic flux lines form closed paths. This is very important. You have to know that flux lines are moving out of magnet from the north pole and start rotating to the south pole. And inside the magnet itself, it will move from S to N. So it's like electricity, guys. If the current is flowing, it has to flow in a circle, in a circuit, closed path. The same is here. Any magnetic flux lines have to flow in closed paths, as you can see here, guys. What will happen if we have a separation between the two poles? So this is here, two poles connected together now, or this can be just one permanent magnet composed of N and S, as you can see. What will happen if you cut or break this permanent magnet? Actually, it will have two separate permanent magnets. So if you cut, for instance, from the middle like that, this will form two other magnets like that. So here is N, so this would be N as it is. This side is S, this would be S as it is, but this will be a north and this will be a south. So this is now, guys, how the or the feature of any permanent magnet. If it is broken, it will create another pole. Why? Because still the magnetic flux lines are stored inside this magnetic material. This is permanent magnet, includes magnetic flux all of the time. So if you break it, it will create the polarity in the broken part like that. And still the flux can go through the magnets like that. And here inside will move from N to S by the same way. So this is, guys, one flux line simulation if we break this magnet. If we have two magnets like that, guys, we need to understand the concept of how the magnetic flux lines are moving. So firstly, you can see that in the middle here, the flux lines may be straight. If you go to the edges of the magnets, you can see that you have like a parabolic path. It's not linear path like the other path we have here in the middle. Okay, so this is the shape of the flux lines. So what is the feature of these flux lines? The feature of any flux line, guys, are, firstly, the flux line all of the time lead to reduce its path. So it's like the rubber wires. You know, the rubber, if you stretch the rubber and leave it, it will return back again. So this is the feature of the rubber. The same is for the magnetic flux lines. For that, guys, if you try to move these two permanent magnets far a bit, they will be attracted again. Why? Because the flux lines in the middle all of the time would like to reduce its path, reduce it until being zero. So this is the feature of the magnetic flux line. So this is one feature. So it leads all of the time to reduce its path or select the lowest path. Another feature, guys, is if you have small distance, the force between the two magnets will be strong, or the force will be higher. If you move these magnets far by like higher distances, okay? So in this case, these flux lines will be very weak until being disconnected or cut. So in this case, there will not be any force anymore. So this is the other feature of the flux line. So again, if the flux lines are short enough, so it will be strong enough. This is one thing. Another thing, the magnetic flux line all of the time would like to reduce its path. And this means, guys, if you have one magnet fixed, which means it's not free to move, and the other magnet is free to move, so this means this magnet will be attracted in this direction. Okay, guys, so this is another feature of, or another phenomena that we can use from the magnets. We can use it in order to make any kind of motion in our machines. Okay, so this is an example for a linear machine, for instance. Okay, guys. So here we just remember together the features of the flux lines and what the meaning of flux lines in permanent magnet and what is the feature of a permanent magnet. If we break a permanent magnet, it will create two other permanent magnets and so on. Now let's go more in deep, guys, and see the relations and magnetic laws we have in electromagnetics, and we will use it for sure in our examples and our machines. So let's start firstly with knowing the parameter H, or magnetic field intensity. So like any current, guys, currents, if the current increase, so this is called intensive current or high current. The same is for flux, guys. We have what's called magnetic flux intensity. So if the flux is intensive, it will have high number of intensity. So this is called magnetic flux intensity. When a conductor carries currents, if a conductor, any kind of wire, carries current, electrical current, a magnetic field is produced around it, as shown in the figure here, guys. So this is according to Maxwell right-hand thumb rule. Okay, so this is Maxwell rule. So Maxwell says if you have a carrying current conductor, a magnetic flux will flow around this conductor in the direction of the other fingers. So this is called Maxwell rule. Okay, guys, or Maxwell right-hand rule. Okay, so assume that you have, let me, guys, jump this part to the next slide and come back again here. Here, for instance, assume that you have a certain magnetic material with cross-section area A, and you have some flux lines are moving inside this area. So due to a permanent magnet or due to any electromagnet, you will have some flux lines moving and crossing a certain area. So what are the quantities we have here in this case? So firstly, we have what's called phi, or flux. So the phi is the flux line itself, and it's measured in what's called Weber. So Weber is the unit of measurements of flux lines. These flux lines are gonna move through a certain cross-section area. So this area is for sure measured in square meters. So this would produce what's called flux density. So as you know, guys, density equals the flux lines divide the cross-section area. So this is called flux density, okay? Flux density, and the unit is Weber per square meter. What about the intensity of the flux lines? So intensity, we said the intensity is H, and H is nothing but ampere turn per meter. From where we got this relation, we will discuss it now from Ampere's law, okay? If you have a coil of many turns, as you can see here in this figure, so let me have the laser pen. Yeah. So if you have a coil of many turns like that, and a current is flowing through this wire, so the current is rotating like that, guys. So we expect that according to the right-hand rule of Maxwell, there will be a flux moving in this direction. So this flux here, guys, will be flowing for every turn. So we expect that if we have 2 turns, the number of flux lines will be doubled. If we have 3 turns, it will be tripled. If we have n turns, so we would have n times the flux lines. So this is going to be the total flux lines. So in this case, guys, we can define the other remaining quantities, like for instance, what is lambda? Lambda is the flux linkage. So if this flux, guys, is going to be interacting with another coil, so we will have what's called the flux linkage. And I think you learned that in electrical circuit, and you learn what's called coupling factor, okay? Also, the coil itself, this coil, once you have current flowing and you have magnetic flux here, this is now representing a passive element of electricity called inductance. For sure, you already learned inductance in electrical circuit, but you may not be aware how can you create inductance. So this is the way how can you create inductance. So the inductance is nothing but just wire, and this wire is wound around a magnetic core, and there is a flux passing in this magnetic core in order to make an inductor. Sometimes we may have air coil. So air means you don't have magnetic material. The flux is moving in air, okay? So this is called air inductance, okay? What is the relation between inductance and others? We will learn all of these relations in our session. For sure, the current is the current that will produce the flux in this circuit, so we should have electrical current here. What is the relation? The first relation we need to know is the relation between the flux density and the flux intensity. So the relation is B equals mu times H. Mu times H. What is mu? Mu is called the permeability of the magnetic material, okay? Phi is the magnetic flux lines, and A is the cross-section area. Now, guys, since you have flux moving and you have currents, we need to know the magnitude of what's called magnetomotive force. So the magnetomotive force, guys, from the electricity side, it's equals to N times I. N is the number of turns of this coil, and I is the current that flow in this coil. Also, from the magnetic side, it can be calculated by 2 different ways. The first way is H times L, where H is the magnetic flux intensity, and L is the average length of the flux line. The average length of the flux lines. And phi is our flux lines times reluctance. Actually, reluctance is the equivalent flux resistance of the magnetic material. So like resistance in electricity, the resistance is the impedance of electrical current and DC current in electricity of DC. And in magnetics, the parameter is called reluctance. So flux is similar to electrical current in electricity, and reluctance is similar to the resistance of the electrical wires. Okay, but reluctance is the reluctance or the resistance of the magnetic core. Okay, or the magnetic bath media, whatever is it gonna be, core or air or whatever material. Okay, now we can go back to the previous slide again to discuss this relation. So this relation, guys, is called Ampere's law. What Ampere's circuit law says? Ampere's law says the summation, the integration or the surface integration of flux intensity times dl. dl is the sample or the smallest portion of the average length of the magnetic core equals summation of currents. This is just for one turn. If you have many turns, so it will be multiplied times n. Okay, but here, if you have many coils connected together, and every coil will have its own flux direction, like for instance, you have a coil moving current or moving flux in this direction, and here I2 in the same direction, but I3 making the opposite direction. So in this case, the summation of current would be like that, I1 plus I2 minus I3. So according to what? According to the Maxwell right-hand rule, because as you know, according to the the current direction in the thumb finger, the other fingers will refer to the direction of the flux. Okay, so this is called Ampere's law in case of just many currents with one turn. But in case of many turns, so we would use our relation that we just mentioned here. So instead of just single I, we have n times I, because we have many turns here in this coil. Now, we agreed together that the flux density equals mu times H. So mu is the permeability. Actually, this permeability has two different parameters or two separate parameters. So it's nothing but the multiplication of relative permeability times absolute permeability of the free space. So you know that free space or air will have a certain permeability. So the permeability of free space, which is 4 pi times 10 to power minus 7 Henry per meter. So this is the unit of permeability. So this is the free space or air permeability. And mu r is the relative permeability of the medium or the magnetic material that will be used in the magnetic circuit. So in case of using air core, we don't have cores, magnetic material. So we have just coil with air without any magnetic material. So in this case, mu would be only 4 pi times 10 to power minus 7. And mu r of free space equals 1. Okay. What about the other magnetic materials that we can use? What are the values of permeabilities we have? So for ferromagnetic materials, guys, such iron, such as cobalt, like nickel, the value of mu r varies from several hundreds to several thousands. In magnetic devices like electrical machines, we do prefer to have the permeability, the relative permeability between 2,000 to 6,000. And we will see some examples for that in our sessions. Now, for any device, guys, we would have like some curves or characteristics. So for the magnetic material, the main characteristics we have is called the magnetization curve or the BH curve. So what is the BH curve? It's nothing but the relation between the flux density, B, measured in Tesla, and the magnetic flux intensity measured in ampere turn per meter. So this curve is going to be different according to the magnetic material, because we just mentioned that magnetic materials will have different permeabilities. And we mentioned the relation between B and H is nothing but mu. So B equals mu times H. So here, guys, in this part here, mu is linear. It's constant value. But if you go in this knee part, so it's not constant anymore, and it's going to change or maybe saturated. So this is now the shape of the BH curve of a certain material. So this material here, guys, is called silicon sheet steel. This is one of the preferred magnetic materials used in electrical machines. Another material here is called cast iron. So the cast iron here, as you can see, guys, at the same value of ampere turn per meter, the value of magnetic flux density is very small. For instance, if you have 200 ampere turn per meter, so this means you can have a flux density of 0.1 Tesla if the material is cast iron. But for the same circuit dimensions, if you replace the magnetic core material from cast iron to, for instance, silicon sheet steel, the magnetic flux density would be 1. So it's 10 times the magnitude. So we will relate that later on to a volt. So assume that instead of V, you have volt or induced voltage, EMF, and this represents current. So assume that if you supply a magnetic material circuit with like 1 ampere, it would produce like 0.1 or 100 volts, and another material would be used and produce 1 kilovolt. So for sure that the magnetic material that can be produce more electromotive force is going to be much better. So in terms of the application, guys, according to the application, we select our magnetic material. But take care, for sure, since this material is more efficient, it will be more expensive. So it depends now, guys. We make a balance between quality and cost of any product. So can you imagine that if you would like to have like small device at home, we may not use silicon sheet steel because the device is going to be very expensive, but we can use cast iron. So the price of the device is going to be reasonable, okay? However, for very high power devices, we do prefer to use silicon sheet steel in the magnetic circuits. Now, guys, let's do more analysis on magnetic circuits and see how can we convert the magnetic circuit into an equivalent circuit. So equivalent circuit, guys, this expression, we will use it a lot in our class. So equivalent circuit means all of us are familiar with using electrical circuits. I mean, if I say to you, for instance, we have circuit like that. I have a resistance, inductance, capacitance like that, and I have an AC voltage source here. I'd like to get the current. This is ground, for instance. I'd like to get the current. So I know all of you will say, yeah, we can apply here like Kirchhoff voltage law. So I is going to be V divide the total impedance of this circuit. So R plus JXL minus JXC. So this is going to be the relation that we can describe here. However, if we have a transformer, if we have a motor, and all the material of the motor would be like that, how can we make analysis? So in order to make analysis for any electromechanical or electromagnetic device, we have to convert the magnetic circuit into what's called equivalent circuit. And the equivalent circuit, guys, will be electrical circuit like that. We can use circuit analysis in order to make the device analysis. So this is a concept that we will use for all devices we will discuss in our class. Okay, so let's see, guys, how can we make equivalent circuit for this small example right here. So here, guys, we have a toroid, and this toroid is made of a certain magnetic material. So it has a circular cross-section area of A, and the radius of the average length, so the average length is going to be the center of the toroid. So if you assume that, for instance, the diameter of this toroid is like 10 centimeters, so we will take the average length at 5 centimeters, in the middle, exactly in the middle of the magnetic material. So this is called the average length. Because if you consider the average length here, it would be less than the average length at the outer diameter. So we do prefer to get the average length all of the time, which is going to be in the middle. So for that, we will consider the radius of the average length of this path. So when we have electrical current moving in these wires around this toroid magnetic material, we expect that flux will start moving inside this magnetic material, and we need to make now the analysis and get the relation of this, let's say, small device. Okay, so now let's apply Ampere's law. So we have now the surface integration of H dl equals N times I. So the surface integration, assume that integration of dl is going to be L, and L is nothing but the average length. So the average length of our toroid here is, depending on the radius r, so we can say it's the perimeter of a circle with a radius r, so it's going to be 2 pi r. So H times 2 pi r equals N, which is number of turns of this coil here, N, times I, which is the electrical current flowing in this inductor, this inductance. So this is our relation now. H times 2 pi r equals N times I. What about the magnetomotive force? So the magnetomotive force, now we can say H times L equals N times I equals F, where F is the magnetomotive force. And we can say from this relation, H equals, we can move L here to the denominator of the other side. So it's going to be N divide L times I. And for sure, it's measured in ampere turn per meter. If you would like to get the flux the flux density, you know that the relation between B and H, so you know that B equals mu times H, and mu is mu node times mu r. So we can say now B equals mu times N divide L times I, and measured in Tesla. So this is the relation of the flux density. If you would like to get the flux lines, guys, so we need to make the integration of B dA. So the A is nothing but the cross-section area of our core. So here we don't have the dimensions of the core, but we define the cross-section area as A, so we can just substitute here by A. Now, if you would like to get phi, so we can say phi equals B times A. Let's multiply B, we got in the previous slide, times area, so we can say now phi equals mu times N times I divide L times A, which is the cross-section area. So we can say it's N times I and move the permeability and cross-section area down here, so it will be L divide mu A. Now we can define another variable from L divide mu A, which is the magnetic reluctance. So the magnetic reluctance of a magnetic material is L divide mu A. L is the average length of the magnetic path, mu is the permeability of the magnetic material, and A is the cross-section area of the magnetic material. It's also equals to 1 divide P, okay? And the P here is referred to permeance, so this is another variable. So permeance is nothing but 1 divide reluctance of the magnetic material. Actually, most of the time we are going to use reluctance. We're not going to use permeance in our relations, okay? So now we define another parameter or another variable, which is the reluctance of the magnetic core. Where can we use that? We mentioned in the beginning, guys, the relation of the MMF or the magnetomotive force. We can say F equals N times I equals phi times reluctance equals H times L. So all of these terms can be used to obtain the magnetomotive force. So substituting here again in our relation, so we can say now flux equals N times I divide R, and N times I, which is the ampere turn, which is the magnetomotive force. So this is the relation. So this is going to be, guys, the general relation that we will use in our problems. Now let's see, guys, still we need to convert our circuit, our magnetic circuit, to an equivalent electrical circuit. How can we do that? So in order to do that, guys, we need firstly to understand how or what are the equivalent parameters for between or what are the corresponding variable in electricity. So we mentioned that in electricity, guys, the electrical current is flowing through the elements. Here we have flux flowing through the core. So flux is corresponding to current. Okay? Flux in magnetic material is equivalent to current in electrical circuits. So in this case, you can represent the magnetic circuit by electric circuit, and instead of current, I'm going to say this is flux. The resistance of the magnetic material has a corresponding value of reluctance of the magnetic material. So I can replace the magnetic core reluctance by a resistance like that, and I can use, instead of resistance, I can use the reluctance value. The supply volt or the EMF we have in electricity, it's going to be corresponding to the magnetomotive force in magnetic circuits. So now, guys, we can convert the magnetic circuit to electrical circuit, and we can use electrical circuit analysis. So if I have this circuit here, guys, and I would like to make a relation, this is very, very simple circuit. So I can say E equals I times R. So similarly, I can say here from this circuit, I can say F equals phi times reluctance. So this is, guys, the analogy between magnetic circuit and electrical circuit. Okay, so we will see, guys, some examples and how can we convert the magnetic material or the magnetic circuit into electrical circuit. For instance, if I would like to make that for this circuit, so let me take a copy of this one right here. Make another small slide here. So I can say here, guys, how many sources of current we have? Just one, because we have just one coil, and this coil will be wound around this magnetic material. So we expect that we have just one flux lines moving inside this core in this direction. So this is flux phi. And for sure, this would have a magnetic reluctance, and we calculated this reluctance based on the radius of the toroid we have. So I can say now, guys, this is equivalent to that electrical circuit. I have just one source. This source is going to be N times I, where N is given, and I is the electrical current. And then we have just one symmetrical shape of core. So this would have just a single reluctance. So this would have only a single reluctance connected to that source. And this is our reluctance. And we mentioned this is L divide mu times area. L is 2 pi r, so we can substitute that here. 2 pi r, this is the radius we have, divide the mu area, and the area cross section is given here. Okay, guys, and for sure the flux will be moving here. So if you have these numbers, Ni and reluctance, if you calculate these numbers, you can say easily now, you can apply Kirchhoff voltage law in this circuit here, and you can say phi equals Ni divide the reluctance, which is 2 pi r divide mu a. So this would give you the amount of flux lines in Weber. So this is the way, guys, how can we convert a magnetic circuit into electrical circuit. So this is a very simple magnetic circuit. You may have some complicated circuits, and we will discuss some of them in our classes in the next session. Okay, but this is, guys, how can we make an equivalent circuit. Now, all of our discussion now, guys, is for a magnetic material when we supply it by a DC current. So this is called the DC magnetization curve. This is called DC magnetization curve. For AC, guys, we will have not a simple curve like that, or this curve will be extracted from what's called pH loops, and we can discuss this maybe after 2 classes. Okay, so for any magnetic material, guys, in order to make analysis, you have to know the BH curve. So the BH curve is nothing but the relation that we have here. So this is the BH curve of the silicon steel, of the cast steel, of the cast iron. Okay, so if you like to make analysis for any device, any electromechanical device, you have to have the characteristic of this device, the BH curve. Okay. Now, we need to elaborate more about the meaning. So, here, guys, in this part here, guys, we expect that the reluctance of the material here is low. And here we expect that the reluctance is high. It's like the relation between V and I. So this is represent volt compared to volt, and this is compared to current. If you imagine with me, guys, you have a resistance that makes a relation like that. I'm going to say this is V, this is I, so V divide I, so the slope here is going to be for R, so I'm going to say this is R1. If you have another resistance, R2, which one is higher resistance, R1 or R2? You're right. So simply, you can just flow a current vertically like that. So this means here you have high volt with the same current. Here you have low volt with the same current. So this means this is low R, this is high R. For that, guys, here we have low reluctance and here we have high reluctance. And this is called the saturation part. So we do prefer to have low reluctance in order to reduce the losses of magnetics. Okay, nice. So the magnetic material shows the effect of saturation in the BH curve is called magnetization curve. And this magnetization curve, guys, we will use it in a lot of devices in our course. The reluctance of the magnetic path, guys, dependent on the flux density. It is low when B is low and high when B is high. So we expect to have low at low value of B. So here is low value and here is high value. Okay. The magnetic circuit differs from the electrical circuit in this respect. Resistance is normally independent of current. And the electric circuit, whereas reluctance depends on the flux density in the magnetic circuit. So it's just like the basics, guys. So the magnetic reluctance depends on the flux, but the value of the resistance is independent of current. So it's just because the like the features of electricity and the feature of magnetic. Okay, but we just make the analogy in order to try to make simplify the magnetic circuit in order to be solved as electrical circuits. Okay, so later on, guys, we'll discuss the AC magnetization and see how can we produce this BH curve from the AC or the BH loops of the magnetic material. Now, let's discuss one more thing in our class today, and we can elaborate more in solved problems in the next session. So here, guys, we have an example for a magnetic circuit. It represents a motor. So can you see here, guys? We have here two poles. So assume that this pole is N and this pole is S. And as you can see, flux lines are moving here and will rotate inside the core and return back again, and so on. And you can see here you have gap. This is air in between this magnetic material in the middle, this one, and the outer one. So you have here air gap. Let's make the air gap in different color. So you have here air gap in between this magnetic core. Okay. So in electrical machines, the rotor is physically isolated from the stator by air gap. This is for two reasons, guys. First reason is to have air gap power, because the air gap can store energy. Second reason is in order to allow this rotor to rotate. Otherwise, if you don't have air gap between stator and rotor, how the machine will rotate? So we have to have air gap in our electrical machine. To maintain the flux, to maintain the same flux density in the air gap will require much more MMF than the core, because the air gap will store energy and this will require more current. So in order to store air gap energy, you have to provide more power and more MMF from the supply. More MMF, and you know that MMF, we mentioned that MMF equals N times I. So this means for the same number of turns, you have to produce or provide more current in order to reach to the required MMF. If the flux density is high, the core portion of the magnetic circuit may exhibit a saturation effect. However, the air gap remains unsaturated. So this is one advantage of the air gap, guys. The air gap, there is no saturation for the air gap. So whatever flux, it can increase if you have air core. Okay. So the relation for the air gap permeability is linear, because we mentioned that for free space, mu r equals 1. So if you have B and H, this is B, this is H for air, so the relation is going to be unity, which means this is the relation. There is no any saturation for the air gap. A magnetic circuit having two or more media, such as magnetic core and air gap, is known as composite structure. So we have, guys, all rotating motors and generators, it's considered as composite structure because we have air gap in these devices. For the purpose of analysis, a magnetic equivalent circuit can be derived for the composite structure, and we said that all devices we have, guys, we have to make an equivalent circuit in order to make this analysis. So this is a quick example, guys. So we discussed another example for a magnetic circuit to convert magnetic to electrical circuit, but here we have air gap. So we have now another shape. So I have here one coil, I have one magnetic core, and a certain air gap here in between. So in this case, guys, we have a source here. This source will provide supply to produce current. You have number of turns N. So you will have a magnetomotive force source equals N times I. So this is N times I. The flux will start moving inside the magnetic material. Assume this is the direction of the flux. So it will move in the same material until this point. It will have another media. So now you have a certain reluctance for the core. So this is the first reluctance. Then the flux will move here in the air gap. So it will see another reluctance. So this is the reluctance of the air gap. And since it will continue again in the same core, so we can consider the reluctance of the core according to the all core dimensions here and consider it in this reluctance. How can we calculate these reluctances now? Simply, reluctance of core equals L core divided mu core A core, where L core is the average length you have here. A core is the cross-section area of this core. It would be given. Is it circular? Is it square? Whatever the dimensions, it will be given, or given as a number in square meters. So this is the cross-section area. And then the flux will travel through the air gap. So we need to calculate also the reluctance of the air gap. So if you go to the air gap, you have Lg, the length of the air gap, this very small length of the air gap, divide, we will not consider the mu of core here because there is no core, it's just air gap, so this is mu node, but take care, mu c here is mu node times mu r of our core. So the relative permeability of the core times mu node, but here we have just mu node. Okay. So these are the two reluctances we have. Once you got the numbers of the two reluctances, you can have it here in the circuit. The number of turns and the current would be given also, so you will have this supply. So now if you would like to get phi, you can use Kirchhoff voltage law here and calculate the flux. After you calculate the flux, which flux you have calculated now? We calculated the flux phi here. I have a question here. If the same flux moving through core and air gap? Yes, exactly. So it would be the same. Because as you can see electrically, our core and our gap are connected in series. And the flux is similar to current, which means it's connected now or flowing now in the series elements by the same way. So flux will be the same. So I can say phi gap equals phi core. However, if I would like to get the magnetic flux density for the gap and for the core, is it going to be the same or not? So you know that B equals phi divide A. So I can say B of core equals phi core divide A core. And BG for the air gap equals phi G divide AG. Now, this is a concept. We said before, guys, if you have flux lines moving between two poles, we expect that if the flux lines are moving here inside in a certain cross-section area A, when it starts traveling in the air, it's not going to take the same area. It may have some like different parabolic path like that. So the area here would be different. However, we consider that this area of the air gap is going to be the same as the cross-section area of the material if the length of the air gap is small. So this is one assumption we used to do all of the time in our small air gap cores. Okay, so we can say since AG equals AC, and this is approximately, so this is approximation, guys. So in this case, we can say the flux density in the gap equals the flux density in our core equals phi divide A core. Okay, guys. So let's stop at this point today, and next session we will continue discussing our magnetic circuits. Thank you so much, guys, and have a nice weekend.